Okay, so I'm going to be talking in this video about differential equations. So a differential equation is some relationship between an unknown function which we're trying to find and its derivatives. So for example, we could have something like x prime equals 3t squared plus 2t, and we want to figure out what x is. Well, in this case, we can do this using the techniques we saw in the last lecture. We can take the antiderivative of both sides. So we know the antiderivative of this function using the inverse power rule will be t cubed plus t squared plus some constant. So this is sort of the simplest example of a differential equation we can come up with. We just have x prime equals some function, and we can solve for what that function is by antidifferentiation. But sometimes there are more complicated examples. So other types of differential equations might be something like this. So here, if we try to take the antiderivative, the function x, which is what we're trying to find, appears in more than one place. There's an x prime here, there's also an x here. So if we try to take antiderivatives like we did in the first example, then we'd have an antiderivative of this unknown function, and that wouldn't really help us. So differential equations like this require more complicated methods in order to solve, and you could have even more complicated things, like something like this. And in general, differential equations can be quite difficult to find a solution to. And so in this class, we're going to be looking at only sort of the more straightforward examples where we can write down a solution relatively easily compared to some of the equations like, say, this, for example. So when we're looking at differential equations, you'll notice that here there's this plus c, some constant that we don't know. So in other words, we're able to determine x up to this constant. So in general, differential equations can have lots of solutions because there might be some constants that we can't determine just from the equation itself. So we say the general solution to a differential equation, which I'm going to abbreviate as DE, is the family of all functions which satisfy the equation. So by satisfy the equation, I mean that we take the function, we plug it into this equation here, and we see if both sides are equal to each other. So for example, if this was our x of t, this t cubed plus t squared plus c, we'd plug it in here everywhere we see an x, and we'd see if the equation is satisfied, and it would be in this case. So in that case, we would say that t cubed plus t squared plus c is the general solution to this differential equation. So if we somehow were to pick a value of c, like let's say I pick c equals 1, then I would get a particular solution to the equation. So it would be one of many possible solutions. So let's look at another example. If we have x prime equals some constant times x, so notice in this example we have the unknown function x on both sides of the equation, so we can't solve this problem by antidifferentiation because we don't know the antiderivative of x. We don't even know what x is. So this one is more difficult to solve. We will discuss a systematic way to do this later in the class, but for now I'm just going to propose that the general solution is x of t equals a constant times e to the kt. So k is the constant k that appeared in my equation, and c is a new constant that shows up, sort of like the plus c up here. So how can we verify if this is actually a solution or not? Well, we plug in x of t into my differential equation and see if it works. So I have to check, is the derivative of x of t equal to k times x if I make this choice. Well, if I plug in what x is, then I have the derivative of c e to the kt should be equal to k times c e to the kt. And if we actually take this derivative by the chain rule, we'll get this. And so indeed, both sides of the equation are equal, so I verified this proposed solution actually does solve the equation. So this is a common equation known as the exponential growth equation, and for now this you should just recognize if you have this equation, the solution will look like this. Okay, so one thing that you may have noticed is that this constant c, we don't know what it is, so we don't have a unique solution. We have an entire family of solutions. Sometimes, though, it would be nice to say that we have just a solution to a differential equation. And so, in order to get a unique solution, we need to specify what's known as an initial condition. So an initial condition gives us additional information about the function, which lets us specify which solution out of this general solution is the one that we want. So you would tell the value of the function at some point. For example, x of t0 equals some value x0, and t0 and x0 would be things that would be given to you. So if you have a differential equation together with an initial condition, it's what's known as an initial value problem. And if we have initial value problems, then we can solve for the solution to the differential equation uniquely. So let's see an example of how that would work. Suppose I have the differential equation x prime of t equals sine of t, and I'm told that x of pi over 2 is equal to 1. So the procedure for solving an equation like this is first to find the general solution. And the way we can do that, since x only appears on the left-hand side, we can just take the antiderivative of both sides to get the x of t is equal to the antiderivative of sine of t. And this gives us negative cosine of t plus c. So this is the general solution. To find the solution to the initial value problem, we use this extra condition that x of pi over 2 equals 1. So if we plug in pi over 2 to our solution, we get that 1 should be equal to negative cosine of pi over 2 plus c. Cosine of pi over 2 is equal to 0. So that means that c is equal to 1. Now that we know c, we can say that the solution to the initial value problem, which is often abbreviated as IVP, is going to be x of t equals negative cosine of t plus 1. And this is the unique solution to the initial value problem. Alright, so these are some examples of differential equations. So if you have one like this, where it's just x prime equals a function of t, then you can solve it by taking the antiderivative of both sides. You also should know how to solve equations like this. You can just memorize that if the equation looks like this, then the solution is a constant times e to the kt. So these are really the only two types of equations that I expect you to be able to solve by hand. What I do expect is if I give you some equation, you can verify if something is a solution or not. So for example, let's suppose I give you the equation x prime equals sine of t plus x cosine of t. And I want to verify that x of t equals t sine of t is a solution. Well, we have to plug this equation in over here. So let's see here. Sorry, this is not supposed to be cosine, this is supposed to be cotangent of t. Okay, so now that we have this, we can try to plug into this equation and see if it works. So x prime, we need the product rule, so the derivative of t gives us 1 then times sine of t, plus derivative of sine of t is cosine of t times t. So this is the left-hand side of the equation. This is x prime with this choice for x. Then the question is that equal to sine of t plus x cotangent of t? So if x of t is equal to this, we can plug in x here. So this is sine of t plus t sine of t. Now remember the definition of cotangent. It's cosine of t divided by sine of t. So the sine of t's cancel, and we see that indeed both sides of the equation will give us the same thing. So therefore, this proposed solution is a solution to this differential equation. So how did I get this solution? Well, that's not something that I'm telling you, but at least we know that it is a solution once this is given to us. Okay, so everything I've shown you so far are examples of first-order differential equations because there was only one derivative appearing. But you can also have equations that have more derivatives in them. So if you have something like x prime prime plus 3x plus t equals 0, this would be called a second order equation because it has an x double prime appearing in it rather than just an x prime. You could also have something like x triple prime plus x double prime plus x cosine t equals 0, something like this. This would be a third order equation because we have a third derivative appearing in the equation. So in general, the order of equation is just the highest derivative that appears in the equation. And so we're not going to go over really how to solve higher order equations in this class, but again, you should be able to verify if something is a solution or not. So for example, suppose that I give you something like x double prime equals negative x, and I want you to verify that a sine of t is a solution, where this a is some constant. Well, you would take the second derivative of this function. So the first derivative is a cosine of t, the second derivative is negative a sine of t. So we'd have negative a sine of t, and that would have to be equal to what's on the right hand side, but since that's just negative x and x is this, we immediately see that the equation is satisfied. But also b times cosine of t, where again b is some constant, is also a solution. We can see this because the derivative of cosine of t is negative sine. The derivative of negative sine is negative cosine. So if we plug into the equation, we have negative b cosine of t equals negative b cosine of t. So the equation is indeed satisfied. So this is a general property when we have higher order equations. If we have a second order equation, we expect to find in some sense two different solutions. In this case, there is both a sine of t solution and a cosine of t solution. And if we had a third order equation, you would typically expect to find three different types of solutions. So I'm being a bit vague about what I mean by different types. In some sense, you might say, well, look, here there's already infinitely many solutions because this constant could change. But I guess the point is that this is one family of solutions where there's only really varying by a constant. This is a very different family of functions. It's cosine instead of sine. So if you take more math classes, you'll learn more precisely what makes these things different in some sense. And why we distinguish that this is two types of solutions, even though in some sense there's infinitely many functions to satisfy the differential equation. So we would say that the general solution to this equation is x of t equals a sine of t plus b cosine of t. So since we have two possible families of solutions, we have to take a combination of both of them for the general solution. And notice that our general solution has two unknown constants in it. So if you wanted to find a solution to an initial value problem, you would need not one but two initial conditions. So for example, if I have the same equation as above, x double prime equals negative x, and I want to find a solution to an initial value problem, I'd have to be told, say, x of 0 equals something, maybe 0, and also in some other information about x. So for example, x prime of 0 equals 1. Then I could solve for a and b. So with this example, I would plug in 0, x of 0 equals 0. This implies that b is equal to 0. Then I can take the derivative of what's left, which is just a sine of t. So then I'd have x prime equals a cosine of t. And I know that x prime of 0 should be equal to 1. So if I plug in 0 here, I get that a is equal to 1. So my solution with these initial conditions would become x of t equals just sine of t. So those are our higher order differential equations. So that's really all that I want to go through as far as differential equations in this video. In class, we'll go through several examples of doing word problems with differential equations, how you can set up differential equations and do some things like that. And then later in the class, we'll revisit how to solve some slightly more complicated equations than what I've shown you how to solve in this video.